Morning, everyone. Thank you for joining this distinguished webinar series in AI and cybersecurity. Today's speaker is Dr. Annabel Pratt. Dr. Pratt is currently a chief engineer with the National Renewable Energy Laboratory. Her research interests include autonomous energy management of energy resources and flexible loads in buildings and microgrids to support the increase in penetrations of renewable energy resources. She received her bachelor's and master's degree in electrical and electronic engineering from the University of Stellenbosch. I don't know, I think I pronounced correctly, South Africa, and her Ph.D. degree in electrical engineering from Oregon State University. Prior to joining NREL, she was a senior power research engineer with Enel Labs, and previously she was with Advanced Energy Industries, where she developed power supplies for the semiconductor manufacturing and architectural glass coating industries. The title of the talk today is Modernizing the Electric Grid. Dr. Annabel, we are so honored to have you as part of the distinguished webinar series at the University of North Dakota. Thank you so much for accepting our invite, and the floor is yours to share your presentation.
Thank you very much. I will just take a moment here to share my screen. Okay. Great. Well, thank you so much for hosting me this morning as I talk to you about the modernization of the electric grid. So today I'll provide a brief overview of the National Renewable Energy Laboratory and grid modernization, talk a little bit about NREL's laboratory capabilities, and then give one example of a capability that I am responsible for, our Advanced Distribution Management System testbed. And then I would also like to introduce some work we do on grid control architecture. And I'd like to end this with just a few notes on internship opportunities for students at NREL. So the Department of Energy has multiple national laboratories shown on this map, and NREL is located in Colorado. And I'm just going to get... and it is a laboratory that is focused on renewable energy integration. We are at almost 3,000 people. This is a picture of our Golden campus. We have two campuses. This is our largest campus. And I'll just point out this building on the right is the Energy System Integration Facility that I'll talk about later, and where the testbed is located. You're primarily funded by Department of Energy, but we work in partnership with industry, academia, and government. So we have more than 900 active partnerships. And we work in renewable power, solar, wind, water, geothermal, sustainable transportation. We have a large effort in biofuels, energy efficiency as applied to buildings, manufacturing. And then energy systems integration is where my work falls around grid integration, hybrid systems, and then security and resilience. So just a quick overview. I think to many of you, this should be familiar territory, but our grid is changing. We have renewables making up a larger share of the energy mix, and many of those are at the grid edge, so within the distribution system, not large-scale generation anymore. And energy isn't just passively consumed at the grid edge anymore. There's some generation in the form of PV panels. It can be stored in batteries, and fuel cells might be coming our way in the future. And then business models are also changing, where there are even efforts around transactive energy at the edge. So we're looking at a grid that is changing, and we need to continue to manage this to deliver affordable, clean, reliable power to customers. Here is maybe a slightly different view of the same story, talking about how our current system has large synchronous generation and centralized control. And we're moving towards a much more complex power system with distributed resources And therefore, our control approaches to this power system will need to change as well. We also have increasing levels of power electronics-based variable renewable energy. And a key component there, and I won't go into this too much today, but a big part of what we are looking at NREL is as we move from a power system that is primarily large synchronous generation with inertia towards a more power electronics-based power system where we lack that physical inertia, it changes how we operate the grid. And again, it's not really within today's the scope of today's talk, but it is a key component of work we are doing at NREL. There's more use of communications, controls, data, and information. And this being a cybersecurity group or topic area, I know that you're really dialed in on this data and information side. And I'll just say right now, I do not come from a cybersecurity side, but more from a power electronics and power systems side. So again, I won't go into much detail on this, but recognize that that is also a key challenge. And I'll briefly mention a key capability at NREL later that is focused on cybersecurity. And then different technologies, electric vehicles, distributed storage, flexible loads, so more complex to control, which is why I'd like to end today's talk with giving an example of one project that we're working on where we're looking at distributed control for this complex grid in the future. So in terms of NREL's laboratory capabilities, we recently, within the last year or so, launched an initiative that we call Advanced Research on Integrated Energy Systems. And the focus here is really proving what works in a realistic laboratory environment before field implementation. So really helping to de-risk implementation in the field of new technologies. So one way of looking at ARES is to look at different scales. So again, I mentioned we have two campuses, and in terms of energy and grid integration, the Energy Systems Integration Facility where I sit is our key laboratory space where we look at these kinds of challenges. And here we can go up to about 2 megawatts is the capability we have for devices that we evaluate and integrate here. Then our other campus that I'll give a little bit more information about as we go through this is called Flatirons. It's about 45 minutes from here. Historically, it was our National Wind Technology Center, but now it really has expanded its scope. And they have also upgraded our capacity there so we can test systems up to 20 megawatts. We're actually just below 20 megawatts to meet interconnection requirements with Xcel Energy. And then we have what we call our virtual emulation environment. So that would allow us to take experimental setups that we have at either or both of these facilities, but scale them up through emulation, so large-scale simulation. And then if we think about controls, I'd like to overlay this with the type of grid control systems that we often hear about and that I'll mention today and where they fit. So starting at kind of the lowest scale here, not local device control, but that first level of aggregation is often a home energy management system or HEMS, or for commercial buildings, a building management system. So in ESIF, we have built up capability to emulate buildings and their control systems. And then these might then be collectively combined into a microgrid. So there is a kind of space for microgrid controllers. And then as you move to the distribution system, not many utilities have a distribution management system, and even fewer have an advanced distribution management system. But I list them here because we do anticipate that the deployment of these controls will expand in the future as utilities have to deal with more and more renewable energy and all these different devices within the distribution system. So the next scale of control is this distribution management system. And that is now more and more often coupled with a DER management system, or DERMS, to manage all the DERs within a distribution system. So this is, again, this distribution system scale. And here we get into the tens of megawatts. And then if you scale it up to transmission system, you get to the transmission energy management system. So these are kind of the traditional levels of control and their purview within the grid. There's then also work to say that we should look at this more holistically and in a more integrated fashion and break down some of these silos between distribution and transmission. And with this more complex power system with more distributed devices that are more active, there's work in this area of how do we apply distributed hierarchical controls to manage this power system into the future. So that's kind of the landscape here. This is just one more view with a couple of photographs, just again depicting that at ESIF, we're more looking at building and microgrid scale up to about 2 megawatt and kind of single feeder. And then as you go to more distribution system and transmission system scale, you get to our facility where we have larger capability up to 20 megawatts. And then that can be integrated with a virtual emulation environment. This is just a graphic that shows some of the capabilities at our Flatirons campus. So we have a 20 megawatt substation. It was just upgraded. We have a 5 megawatt dynamometer and 2.5 megawatt dynamometer. We have several megawatt scale wind turbines that can be used for testing. We are establishing a megawatt scale hydrogen system. So both electrolyzer and fuel cell are being deployed. A large PV array, we have load banks, we have batteries, and then we also have these research pads where some of these are fixed equipment that we as ESIF provide for experiments, but people can bring in their own battery system or fuel cell system and set it up here, and we can run some tests. And then in the center here, showing that we are, CGI stands for Controllable Grid Interface. So this allows us to do hardware in the loop experiments with all of this hardware. So really, incredible investment by the Department of Energy in this facility. And then stepping back to the energy system integration facility here at the campus that I'm at, we have several laboratories, and they could have focus areas in terms of energy storage or power system integration lab, where I tend to work a lot. But we also have, these labs can be interconnected, so you can run experiments using equipment from different laboratories and run integrated experiments. And here are just some photographs showing some of the capabilities. This is the fuel cell electrolyzer setup in our hydrogen area. We have several real-time simulators, Opal shown here, RTD as shown here, that help us with hardware in the loop experiments. We have a laboratory where they're really focused on electric vehicle integration, and the other side of the laboratory is looking at commercial building. This is an ice storage unit, for example, and here are some refrigeration cases for work we're doing with grocery stores and using the thermal mass in grocery stores to provide some demand response within the distribution system. And we also have an outdoor area, vehicles, and this really will change based on what experiments we run. So we have some diesel generators available, but people will bring in different batteries, et cetera. And if they're larger, over a megawatt or so, they're typically set up outside. So, large facility, about 200 staff and research partners working here, and you're looking at cybersecurity, resilience, grid systems integration, buildings, etc. So again, ESIF was completed in 2014, so we've been up and running for about 10 years in this facility. Oh, and let me just mention, this is a user facility, meaning that, yes, we can use it for our research, but outside entities can use the space here and pay for space and staff time to use some of these capabilities. And then, as I mentioned earlier, just wanted to point out a cybersecurity related capability that we have here at ESIF. And again, not my area of research, so not something that I work on directly, but I put in the web link here, and we'll make the slides available so that you can learn more about this. But the idea here is that it's part of this overall Aries platform, and we can integrate physical devices from across the laboratories into this virtual environment. And then you can do studies with hardware, controller, and human in the loop. So one example might be that you might set up a system with these different controllers and try to launch an attack and evaluate the cybersecurity of that system. Again, just not my topic of expertise, but something that is fairly well described on our website, and that you can follow up on from there. So what I do want to highlight here is just one of our capabilities within ESIF that I am responsible for. And this is what we call our ADMS testbed. And ADMS, again, is our Advanced Distribution Management System. And that's at the scale of control of a distribution system for a utility. And this was originally established about 5 years ago with the goal of accelerating industry adoption of ADMS, because we believe that, again, as there are more and more renewables and complex loads and more interactive loads within the system, we need controls within our grid that can manage those appropriately, and that this level of technology will become more and more necessary for utilities to continue to operate. So one side of it is to improve normal operations with high levels of DERs, but also improving resilience and reliability. One of the key functions of an ADMS is what's called fault location isolation and system restoration. So after that, there is an event, these control systems can automatically identify where a fault is, isolate the area around it, and then start to restore the system so that customers have a shorter time of loss of power. So it's both normal and stress conditions that we want to evaluate using this. So what the testbed does is it represents a distribution system. So we are then able, when it was originally conceived, the idea was to bring in a commercial ADMS software. And when we deploy it here at NREL, it thinks it's operating in the field. We use industry standard communications interfaces. So it is set up just as it would be for that utility in the field. But instead of a real field situation, we have a real-time simulation of that system. And we can also integrate hardware through hardware in the loop techniques where it makes sense. If it's a project that really wants to look at the use of batteries, we might integrate a battery inverter with the real-time simulation. So again, originally conceived very much with the focus on ADMS. As the years have gone by, DERMS, DER management systems, have become more prevalent. So we also now are starting to see projects where we have a virtual power plant or a DERMS solution that works in conjunction with an ADMS. But this allows us to evaluate the operation of an ADMS on a specific utility system. So we partner with utilities and ADMS vendors. We set up this realistic laboratory environment, simulate real distribution systems. We can integrate hardware. We use, DNP3, Modbus, whatever that utility uses in the field. And we also, in terms of analysis, we have some advanced visualization capability that we can use to understand the results better. So again, key capabilities is the multi-time scale co-simulation. So for large systems, the real-time simulators cannot handle, and it keeps growing. A few years ago it was 2,000 nodes. Now you can go up to about 10,000 on distribution systems, but still you can reach a point where you can't run all of it on a real-time simulator. And then we can co-simulate with quasi-steady state time series simulations to be able to simulate larger systems. And again, hardware communications. And on the communications, again, because that's more of a focus here, I do want to mention that for a few years, we continued to talk about integrating some network simulators such as NS3, and we have not, up to this point, the projects we've had have just more focused on the functional side. But we've had some conversations over the past year, and we're actually in the process of doing some integration between the cyber range that I mentioned and the ADMS testbed to kind of bridge those, where my team is mostly focused on the functional aspects and the control aspects, but partnering with the cyber team to look more at the communications and what if these communications are compromised between the control system and the simulated distribution system. And here is just a few photographs of what you would see if you came to visit our laboratory. And what we show here is these are ADMS user interfaces. These are a couple of different products just to make the photo interesting. Again, the ADMS is software. It runs on a virtual machine. So really all we can show there is the user interface. In this case, this is an OpalRT real-time simulator that we were running with. And then we can integrate various pieces of hardware. We have some cab bank and LTC controllers over here, some grid edge voltage management devices from a project, solar inverters, battery inverters, whatever makes sense for the project. And then we've developed some real-time visualization and also post-processing 3D visualization capabilities that we can use. And how we typically work in these projects is a utility might have a question or a challenge of, can the ADMS manage voltage under high battery penetration, for example, or how does DER systems influence system restoration performance? Or a vendor might want to demonstrate a new functionality. So we define what we call a use case project, define the test plan. We need to understand the vendor equipment capabilities. We configure our test bed with field data input from the utility to model that distribution system realistically, with technical support from the vendor, especially when it's an ADMS that's new to us, and then through result analysis and dissemination. And then on the testbed, I just want to hone in on that a little bit. So we determine our test scenarios and our test plan, and then we have multiple work streams in terms of what simulation tools do we need to use. If we're looking at faults on the system, we want to use an EMT, an electromagnetic transient simulation. But if it's voltage management or demand reduction, we may want to run a quasi-steady state time series simulation. We see whether there's specific hardware we want to integrate, and then we need to develop those power hardware in the loop interfaces and integrate the hardware with our real-time simulator and determine communication needs. And sometimes we need to develop new interfaces. Over the past 2.5 years, we have actually built up 2030.5 communications on the testbed to be able to run that. And that was mostly for the grid controls project that I will talk about a little bit later. And then there's also the deployment of the ADMS. Again, this being a commercial system that gets deployed here. And if it's a new ADMS to us, we go through training and then configure all of that. So it is really integration. System integration is just a huge part of this to get all of this to work together. And yeah, then you execute the test plan, analyze results, etc. So we have to date worked with General Electric, Schneider, Surveillance, Oracle, OSI, and there are really 8 main ADMS vendors. So we've worked on 5 with them. OSI is in progress right now. We are also working with a virtual power plant by Spray. And then we have a project where a utility, they have an ADMS. They want us to evaluate the ADMS and DERMS for flexibility, but their process has been rather slow in finding a DERMS to fit their needs. So we still do not know whose DERMS, but we are on the point of bringing in a commercial DERMS into our testbed. And then we also, now that we have the testbed, again, originally conceived to evaluate commercial ADMS solutions, but we've also had many team members use this capability to evaluate their research controls. And we can, I'll talk a little bit later about GridAppsD as kind of a platform that we can run those on, or just sometimes it's just Python code that we run on a laptop real time to test our fellow researchers' controls approaches. So speaking of controls approaches, I'd like to present just one example of a project that I lead on the grid control side. But again, just generally, there is quite a bit of activity at NREL around advanced controls, and many of them are moving in the direction of hierarchical distributed controls. This specific project, Federated Architecture for Secure and Transactive DER Management Solutions, or fast terms, was funded through the Grid Modernization Initiative of the Department of Energy. And this was really, it was launched about 4 years ago, and the intent was to get multiple laboratories to collaborate, so bring the strengths of different laboratories together. So here we work with Lawrence Berkeley, Pacific Northwest, and Oak Ridge National Laboratories, and also multiple utility and vendor partners. So just another way of describing what we're facing in terms of the grid, we're seeing increasing penetrations of variable renewable energy. And here is a, it's just a chart that shows, hydro has been fairly flat in biomass, but wind and solar is the largest increase. And just a footnote here that in 2020 was the first year that wind produced more energy than hydropower. So just a really different power system from what it was 40 years ago. So residents and businesses need a reliable power grid. So as we deploy more of these DERs, we need them to start contributing to energy and ancillary services to maintain reliable grid integration, because we are taking more synchronous generation offline that has traditionally provided those services. And we know that behind the meter assets can provide significant flexibility, but grid integration can be expensive and add complexity. So there has to be a compelling reason for them to participate, and we need to continue to make it easier for customers to engage with grid services. So for this project, we set out to design and develop a federated architecture that can aggregate and manage a broad range of DERs across the grid for bulk system services. So again, I just want to emphasize this, that these are distributed energy resources, so they are connected at the distribution system, but we need them to provide bulk system services, transmission system services to maintain overall grid stability without negatively impacting the distribution system operation. So we need it to be scalable because we're expecting millions of these devices, and fast management. And DERs can be utility scale or small scale. So you could have your local utility might invest in a battery energy storage system. So it can still be under utility control, but many of these DER, probably the bulk of them, will not be under direct utility control, but rather under the control of the customer. So you need to engage the customer to make a DER available to participate in grid services. We want to support transactive control, seeing that as a kind of up and coming way of managing resources. Aggregation, so many of these smaller DERs today already, you can participate through a third-party aggregation into a wholesale market. And then we also need to be able to work with existing utility management systems. So for a while, it's going to be a hybrid system before we reach this full distributed hierarchical vision that we need to work with existing ADMS solutions. And then what I show here are a couple of grid architectures that Xcel Energy and Portland General Electric were kind enough to share with us for illustration. And what I want to point out, and you can see it on this one a little bit more easier, they really currently tend to think of aggregation in terms of single technologies. So you might have a battery aggregator, an EV aggregator, and that's really how it flows up to the ADMS DERMS level. And here in this one to, kind of aggregation for different technologies, and then a centralized ADMS and DERMS solution is where utilities stand today. But our position is that we don't think that we can achieve scale with this current centralized approach. FERC 2222 order has already been showing challenges with this transmission and distribution coordination and complexity. So we are arguing for a distributed, hierarchical, some people use the term fractal or laminar, but they all have this idea of, you just kind of look at this diagram of a hierarchical distributed control, bringing more of the intelligence to lower levels. And I just show, this is a source from Pacific Northwest. This is from a consortium, Agile Fractal Systems and NREL, just all depicting this similarly in terms of that hierarchical nature. And this is how we believe we can get to scale. So this fast DERMS project, aligns with all these other approaches. This diagram here from PNNL came out of a previous GMLC grid architecture project, where they really looked at grid architecture holistically, and NREL has an autonomous energy systems initiative. So where we think we bring additional value to this field is to explicitly from the beginning say, how do you incorporate third-party aggregators, microgrids, building management system, transactive markets into the controls? Because still many of these assume direct utility control, which just isn't really realistic. So this is the control structure that we are proposing. Again, you can see the hierarchical nature of it, TSO talking to a distribution system operator, but then we're proposing that a natural hierarchical point to aggregate a system is at the substation. So we are proposing that we have a solution here that manages all of the resources within a substation. And this again goes back to this idea of this laminar control. So just a very, what's the word, like classical or, clean way of looking at controls, that there isn't bypass from one level to the other, but this gives us the observability and controllability that we want for this system. And we believe that this should be a network-aware optimization, because you have to be able to look at your distribution system power flow, make sure there aren't overloads or voltage violations when you use these resources. And some of them can be used through an aggregator, and some through a transactive market, and some can be managed directly. So distributed control. And then one other key point is that we are proposing that you manage the power flow at the substation. So really what you want to do from the transmission system point of view, as the transmission system operator looks at this system, it can rely on the power flow to that substation. I mean, in the ideal case, it would be almost like a traditional generator, that it knows what it is going to, in this case, mostly draw from the transmission system versus deliver to it. But most approaches today in terms of DER management will simply manage the DER to achieve a certain goal, but that still leaves you subject to uncertainties in the load. So by managing the power flow to the substation, we believe that we can really simplify this transmission to distribution interaction. So this project, we looked at architecture development. There is a system architecture and reference implementation document available. And then we developed some reference controls that I will lightly touch on. Again, don't have time today to get into the controls details. And then want to tie it back to the laboratory demonstration, because we're using the ADMS testbed to demonstrate the controls developed through this project. So in terms of reference controls, the goal is to provide a firm transmission level resource measured at the substation meter while maintaining distribution service quality. So that's what we set out to do. The main control effort has been around the flexible resource scheduler, and Lawrence Berkeley National Laboratory is leading that effort. And then in order to demonstrate this, we've also developed a simple aggregator. We've developed a building management system that's in partnership with University of North Carolina, Charlotte, transactive market manager managed by Oak Ridge National Laboratory, and this market manager then works with the transactive home energy management system. So we've built up all of these different controls, and I will then just focus in on this flexible resource scheduler. We have three different layers or temporal controls. So the first is day ahead, again, because we are aiming to work with the transmission system more like a traditional generator, where you can tell the transmission system what you plan to do for the next day. You need to perform a day ahead optimization to schedule your market offers, to say this is how much power I will draw, or in some cases produce at the substation level. And this is a stochastic optimization because of uncertainty in DER, in load, and in DER generation. So you put that bid in when the market opens, and then you get your commitment. And then when you start operating, there is a model predictive control that continues to manage the DER set points. And then there is real-time feedback control to minimize the dispatch errors. So this flexible resource scheduler actually works at these three time scales. And then I am just very briefly going to say, the day ahead is a scenario-based stochastic optimization. So this really is, optimization type problem that is defined and needs to be solved in a reasonable amount of time. Similarly, optimization problem for MPC. When you get to real-time control, we are at that substation. We have a dispatch coming from the TSO, and the real-time algorithm, then what it aims to do is to make sure that your actual power at the substation is close to that dispatch. So those are the three levels on the FRS. And then again, we did some work on the transactive market that I am going to skip over in the interest of time. So that now ties back to laboratory demonstration. We want to show that these controls work, and we are using NREL's testbed. So let me just talk through the diagram on the right here of what we are setting up. So San Diego Gas and Electric is a utility partner. So we are simulating one of their feeders. So our real-time simulation is running a simulation of this SDG&E feeder over on the left. Then our controls, so our flexible resource scheduler, transactive market aggregator, we implemented those on GridAppsD, which is an open source platform for grid control evaluation. And I have a slide to introduce that to you a little bit more. But this is one of the ways that we can test research algorithms. We're also integrating with Oracle ADMS. Oracle is SDG&E's ADMS provider. So this is the system that our controls would have to integrate with in the field. And then we also wanted to demonstrate the ability of our flexible resource scheduler to interface with a microgrid. So there isn't actually a microgrid on this SDG&E feeder. We're adding one for the purposes of illustration. And we're actually doing this through remote co-simulation. So ComEd is running their Bronzeville microgrid simulation with their Siemens microgrid controller at their site. And we have a VPN connection with them to do that remote co-simulation. So this is how we aim to demonstrate this year. We are still working on all of this integration. This is the feeder, this is the substation, and all these yellow stars are PV system. It's a very high PV, most of it rooftop PV. System, which is one of the reasons we chose this feeder. What we are adding, again, to demonstrate is the microgrid that I mentioned. We're adding some utility scale PV and utility scale storage. And also we're replacing some of the loads with a few large commercial buildings. So that is the system that we will be simulating. And then because it's a high residential area, and we want to demonstrate the transactive control with a home energy management system, we are using a simulation tool called ocher that was developed at NREL that I'll also just talk about, just in the sense that all of these different tools might be of interest to you as you move forward, and they are available for use. So ocher specifically is a simulation tool for residential buildings. It's white box, physics-based, and it models load flexibility at a high resolution. So it is a reduced order model of a building. So it starts with an Energy Plus model. I think, yes, I have this slide here. So ResStock builds your Energy Plus models, and then there is the ability to reduce that and come up with a simpler model that is better for co-simulation and better for control applications. So this becomes a simulated home within our overall simulation of the system. So we attach it to the feeder model. You can control HVAC, water heating, EV, PV, and batteries. And again, it was really developed with the intent that you can integrate with controllers such as home energy management systems and with grid models. So that again is this ocher tool that's part of our simulation. The other one that I wanted to point out was the GridAppsD platform. This was developed by Pacific Northwest National Laboratory. is an open source platform for ADMS application development. Now, GridAppsD comes with a built-in distribution simulator. We are using it a little bit differently. We are only using the control applications in our setup on GridAppsD, and then instead of using their internal simulation tool, we are attaching it to the test bed. However, our first step in all of this is to use it with their internal simulation to get our initial results. And then, as I mentioned, we're integrating with Oracle ADMS, and we plan to demonstrate wholesale electricity market participation. So that wraps up my overview here of kind of NREL's laboratory capabilities, broadly speaking, and then I honed in on the test bed, and then gave this one example of work that we're doing in terms of new advanced grid controls, and how we use the NREL laboratory capabilities to demonstrate the feasibility of these new controls. And again, this is just one example of multiple efforts, but I'd say most of them are moving in the direction of hierarchical distributed control. So I just wanted to wrap up speaking to a university audience that if this work interests you, this type of work, then just the skills that our directorate are interested in is your power systems, and integration with gas and water is becoming more important. Again, no time to touch on that today, but definitely power systems background. Power electronics, going back to my comment earlier about there being more and more power electronics based resources on the grid, and how that affects the operation of the grid. Control systems, distributed, robust control optimization. And then, when we actually get to the laboratory setups, people who can do embedded systems and firmware, and of course, lots of modeling and visualization and data analytics. So that's kind of the skill set that you would find within our center. NREL offers graduate internships to graduate students. And again, you can just go to nrel.gov on our career site and learn more about it. And it's been a rough few years with COVID, and this year we're so excited to have many interns on site again. But I think for all of them, it's a great experience to come and work and have the ability to work in our laboratory environments. And there is also an undergraduate internship program. This is actually administered by the Department of Energy. And I give the website here, it's called SULI, and it is a way to provide, it's mostly people going into their junior and senior year, and it's year-round. There are 3 terms that you can take to do a SULI internship. And this, again, you can put in your top choices for laboratories, but you really apply to the Department of Energy, and you get assigned to a specific laboratory. So thank you. That is what I had for today. I'm happy to take questions and do my best to answer those.
Thank you so much, Dr. Annabelle, for a well-rounded talk. I know that you started from giving a background about NREL and then touched upon all the open-ended research opportunities or problems within the distribution networks, ranging from modeling, simulation, optimization, functional aspects. So I think it's great that what NREL is doing, but I think let's just see, Jameson, why don't you collect questions while I maybe start asking the first question. And I think I'm also glad that you brought up the share the resources for internship opportunities for students to, go and apply. And I think most of the students, most of them are listening are graduate or undergraduate students, from this webinar. So thank you for that. And this internship opportunities are open for our domestic students, also for international students.
Yes, it is, of course, easier. Oh, as long as they're at a U.S. university. Yes.
Yes, yes,
If that's the
yeah.
question. Yeah, absolutely. It is. We sometimes also bring in interns from overseas universities, and that's a little bit more complex. But for a US university, absolutely. Yeah.
Great, great. And so, okay, let me see.
We have one question.
Yes, go ahead, Jameson.
What are the practical implications in integrating quantum computing and modern grids?
Yeah. So, quantum computing is, again, sorry, it's just not my area of expertise. And actually, my main exposure has been through some interaction with Prakash on a proposal that he is putting together. So there is likely some work in quantum computing at NREL. We have a kind of a high performance computing division at NREL. I think your best bet to see what NREL is doing is just to search nrel.gov. We have a publication site for more information. But I think, Prakash, this is something that you have given some thought to, correct?
Yeah, you're right. I think quantum is gaining attention. We're not there yet for a fully, but I think has some potential to, and from a security point of view. So I still do not know much about it. I'm still also learning. So that's a good question anyway. Yeah. So let's see. And you talked about managing the power flow at the substation level. Is there a reason for that? Rather than looking at more at the different at a microgrid or next. Can you give me some insight on why you stress that point?
So it's really, if you view it from the transmission system, and you think of a transmission system, and if it could either have a generator connected at a node, or it can be a load serving entity. So a load, and traditionally the load was fairly easy to forecast because it was fairly passive. But now that load is, if a distribution system is connected at that transmission system node, that distribution system is starting to look very different. Its load is varying more as it has smart thermostats and water heaters and EVs charging. And then its power flow is more variable with rooftop solar and battery energy storage systems. So it increases the uncertainty of the net load at that node. So what we are saying is, if we can offer a firm like a firm service, a firm offer, and say, transmission system, at this node, we will be drawing this much power over the day. It becomes a resource to the transmission system with less uncertainty. So instead of having a DER management system that manages DERs and aggregators, so the transmission system is trying to manage an uncertain load through aggregators that bypass the distribution system operator. If we combine that at the distribution system operator level and become responsible for saying, here is a known, reliable power profile for the next day, it makes it much easier for the transmission system operator to manage the system. Does that help?
Yes, thank you. And I want to pull up this other interesting question that I have in mind. You talked about this ADMS and all these terms. We don't have much utilities have this larger infrastructure of these type of enterprise to softwares. And you talked about this. Each of those DER fleet are so vertical and silos, and then you have centralized ADMS, and yet we probably need to go into some kind of exploiting the communications between these things, exchange and distributed fashion. What do you hear from your experience from vendors and utilities? How are they? How are they actually?
Yeah,
I know. My question is, how are they receiving that? How in going into the future in terms of yeah.
It varies, like so many things in life. But some companies have really, they have started to put product out there that matches this distributed control architecture. Oracle being one example, which is part of the reason they partnered with us on this project, is because they came to the same conclusion that we will need a distributed control architecture. So they actually now have a product called GridEdge DERMS that is a distributed implementation. Others, such as Schneider, I have found very open to this architecture. But with vendors, they understandably can be cagey about what they're working on. So as far as I know, Schneider doesn't have a product out there. And I don't know if they're developing something, but in conversation with them, you get the head nod of they see it moving in that direction. So my sense is that we will be seeing more of these products, but not from all of them. I think there's also and like I mentioned, there are really only 8 major ADMS vendors. It's a fairly small community, but right now, most power systems can get away with a centralized approach. We're
Great.
future.
I think I know that when I also interacted with our local partner utilities over here, I think pretty much, they do mention that they anticipate the DERMS will impact the distribution operation utilities, but I think they also said something. NERC and ISOs are also trying to figure things out. So do you have any interaction with NERC and ISOs on this?
So I do not directly. Now, NREL does, and some of my colleagues have had the opportunity to present some of this material to them. But the FERC 2222 order that I mentioned was good news in the sense that it recognized the need for using distributed DER, distributed energy resources, to provide services, but it allows for that bypass of its DER to TSO market operator. So, which many of us thought is, will cause problems down the road because it's not a neatly structured laminar hierarchical control architecture, and that it can lead to problems later. So based on that action, they took a certain approach to it that does not fully embrace what we have been trying to promote, which is a well-structured hierarchical control approach.
Interesting. Thank you. Jameson, do you see other questions on your end?
Yes, we have one more. Which specific technologies do you expect to play a significant role in advancing the modernization of grids in upcoming years?
Electric vehicles comes to mind very quickly, especially with all of the legislation that we're seeing to promote the electrification of transportation. That really is just the first one that comes to mind. And then I think battery energy storage systems hold a lot of potential, but I think there is still both a price barrier and, fortunately, we have such high reliability generally for our electricity supply that I think the value of buying batteries for resilience in most of the US is not quite high enough. So I think it can have a tremendous potential, but I think its impact is lower still than what electric vehicles will be because the adoption rates are lower.
Great. Well, since most of our audience are students, what is your piece of advice for them as they're looking at the thesis or dissertation topics? Your title is so nice and short, electric grid modernization, and yet you touched all big concepts in a broad way.
Yeah.
And I But I just want to ask people to hear from your own words to see, what is those couple of big piece of advice that you want to provide to graduate students as they are searching for thesis and dissertation topics, yeah.
So I'll just go back to my power electronics comment that for those students working in power electronics and also in power systems, that power systems, you need to incorporate the impact of the growth of power electronics interfaces in the power system. And to the power electronics side, keep in mind that interaction with the grid. But that field of grid forming inverters, not a term that I've used here, but inverters that have the ability to form a grid. So it's not just tracking the overall power grid voltage and frequency anymore, but can actually establish it. I just think that is a field that there's still great variation in even how grid forming inverters are defined. So that is a ripe area for research. And then the impact on power systems. The controls work will keep coming. I hope that I made a good case here for distributed hierarchical control. And stochastic, I mentioned that a couple of times, the stochastic optimization, but the uncertainty that DER introduces into the power system will need to be dealt with in controls. So if you're looking into some kind of an optimization approach, let's say smart charging of electric vehicles, I would just say make sure that you really think through the uncertainty and the impact and how you can compensate for that within your controls. Then, because it's so much of our work is modeling and simulation.
Sure.
And transmission and distribution co-simulation. So being able to really simulate transmission systems with actual distribution systems connected to them, because what we do today is we model a distribution system and you just put a fixed voltage source for the transmission node, or you model a transmission system and you just put a load profile. And for those who are more in the kind of software side of things, scalable simulations for the entire power system is what we'll have to be able to move to show the impact of these hierarchical systems.
Great. Thank you so much. I'm sure that like I was stimulated by your talk. I am sure there are many students who are actually also appreciate your time and effort for giving us this webinar. Thank you so much, Dr. Annabelle, for your time. And we're going to conclude this webinar. And as a token of appreciation, you will receive a plaque and a certificate from our dean. And we look forward to work with NREL. Please hire our students also.
Please apply.
And yeah, thank you so much. I look forward to meeting with you at some point. And so yeah, you should visit UND too. Yeah.
Thank you so much.
Thank you so much. Take care.
Take care.